Good evening, and welcome back to SleepWise. Tonight, we drift toward some of the strangest and most quietly astonishing objects in the known universe. Places where gravity has gathered itself so completely that even light, the swiftest traveler we know, leans inward and stays. Places the old imagination called impossible, that early scientists doubted could ever be real, and that modern instruments have only recently begun to glimpse faintly against the glow of distant skies. Tonight, we drift toward black holes. The phrase itself carries a certain weight. For many people, it conjures images of cosmic monsters, of ravenous voids, of danger lurking somewhere in the dark between stars. But the truth, as so often in nature, is gentler and more interesting than the legend. Black holes are not holes punched through the fabric of reality, nor drains pulling the universe down into nothingness. They are, in the quiet language of physics, regions where the geometry of space and time has folded so deeply that no path leads back outward. They are not absences. They are extremes. They are what happens when one of the simplest forces in the universe, the patient pull of gravity, is allowed to follow its own logic to the very end. And so tonight, we will set aside the theatrics. We will not hurry through equations or cling to frightening images. Instead, we will move slowly, the way one moves through an unfamiliar room in the dark, letting the eyes adjust, letting the shapes reveal themselves at their own pace. There is no need to understand everything at once. There is no need to remember each name or number. The story will carry us, and the night will hold us as it does. To approach a black hole gently, it helps to begin far from one. It helps to begin with the sky as humans once knew it, long before telescopes and equations, when the heavens were a quiet ceiling of light and the stars seemed pinned in place. From that older world, we will follow a patient thread, through whispered ideas in the 18th century, through Einstein's reimagining of gravity, through decades of doubt and discovery, all the way to the first faint image of a shadow cast against distant fire. Along the way, we will meet event horizons and singularities, spinning geometries and silent giants at the centers of galaxies. We will think briefly about what happens to time near such places and how light behaves when geometry itself begins to lean. And we will end, as all SleepWise journeys do, somewhere closer to home, somewhere softer and more familiar than where we began. If these quiet stories help you rest, you can follow SleepWise and share it with someone who might enjoy drifting off while learning something new. And now, with the night around us and the stars patient overhead, let us begin. For most of human history, the sky was a place of quiet certainty. The sun rose and set with great regularity. The moon passed through its familiar phases. The stars wheeled overhead in patterns so dependable that travelers could find their way by them, and farmers could measure the year by their slow procession. Whatever the heavens were, they seemed to be governed by a kind of patient order. In 1687, that order found a precise voice. In a long Latin work titled Philosophiae Naturalis Principia Mathematica, Isaac Newton set down 3 laws of motion and a single sweeping law of gravitation. Every body in the universe, he wrote, attracts every other body with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Double the distance, and the pull becomes 4 times weaker. It was a simple rule, written in the cool language of mathematics, and it described an astonishing range of things at once. The same rule that explained why an apple falls from a tree also explained why the moon does not. The moon is, in a sense, falling toward Earth all the time. It simply moves sideways quickly enough that it keeps missing. The same rule explained the tides, which rise and fall as the moon and sun pull gently on the oceans. It explained the slow, looping return of comets, including the one the astronomer Edmund Halley used Newton's equations to predict, correctly forecasting its return in 1758, 16 years after his own death. Newton's framework rested on 2 quiet assumptions, so deeply held that they were rarely questioned. The first was that space existed as a kind of fixed and absolute container, the same for everyone everywhere. The second was that time flowed evenly throughout the universe like a single great river. A second on Earth was a second on Mars, on the moon, in the depths of empty space. Within this framework, gravity was strong, where mass was great and where distance was small. Light was treated as something else entirely, a swift and luminous traveler whose nature was still being debated, but which was not generally thought to feel gravity in any noticeable way. Stars shone, planets moved, and the stage of space and time was assumed to remain perfectly still beneath them. Newton himself was uneasy about one part of his own picture. How could one body act upon another across vast empty distances with no visible thread between them? In his private writings, he confessed that this puzzled him deeply. But the equations worked so well, predicting eclipses, orbits, and tides to remarkable precision, that the deeper question was set aside. For nearly 2 centuries, the universe seemed to behave like an exquisitely well-made clock. And in such a universe, the idea of a star whose own light could not escape would have to wait for someone willing to follow Newton's logic into stranger territory. In the late 18th century, in a quiet rectory in the village of Thornhill in Yorkshire, an English clergyman and natural philosopher named John Michell sat down to think carefully about gravity and light. Michell was unusual. He had been a professor of geology at Cambridge before settling into parish life, and he was the first person to suggest that earthquakes traveled as waves through the earth. He also designed the apparatus later used by Henry Cavendish to weigh the world. Michell was, in short, a man comfortable with strange ideas. In November 1783, he sent a letter to the Royal Society in London, addressed to Cavendish himself, in which he asked a quietly daring question. Newton had taught that an object thrown upward from the earth must reach a certain speed, the escape velocity, in order to leave the planet entirely. For Earth, That speed is about 11 kilometers per second. For larger and denser bodies, the required speed is greater. Michel wondered what would happen if a star was so massive that its escape velocity exceeded the speed of light itself. He worked the numbers using Newton's framework alone. He calculated that a body with the same average density as the Sun, but with a diameter 500 times larger, would have an escape velocity greater than the speed of light. Such a star, he reasoned, would still pull on its surroundings, but its own light would never quite leave its surface. From a great distance, it would appear entirely dark. Michel called these hypothetical objects dark stars, and he even proposed how astronomers might detect them by watching how their gravity disturbed the motion of any visible companion stars in orbit around them. A few years later, in 1796, the French mathematician Pierre-Simon Laplace arrived at a similar conclusion through his own calculations. Laplace was one of the great minds of his era, a careful and confident thinker who had reformulated much of celestial mechanics. He included the idea of an invisible gravitational body in the first two editions of his book, Exposition du Système du Monde, suggesting that the largest bodies in the universe might be dark for precisely this reason. By the third edition, however, he quietly removed the passage, perhaps uncertain about how seriously to take such a strange suggestion in a work meant for a wide audience. For more than a century, the dark stars of Michel and Laplace remained a curiosity, a footnote in the margins of natural philosophy. The instruments of the time could not test the idea. Light was not yet fully understood as a wave or a particle, and the very notion of a star whose light could not escape sat somewhere between mathematics and dream. But it had been spoken aloud. The thread had been laid down, and nature, as she so often does, was patient. She would wait until the language of gravity itself was rewritten before that thread was picked up again. A century passed before the dark stars of Michel and Laplace returned, transformed almost beyond recognition. The change came not from new telescopes, but from a new way of thinking about gravity altogether. In 1907, while working as a patent clerk in Bern, Albert Einstein had what he later called the happiest thought of his life. He realized that a person falling freely from a roof would not feel their own weight. Gravity and the absence of gravity in that moment would be locally indistinguishable. From this small insight grew the equivalence principle, and from the equivalence principle, over the next 8 years, came general relativity. Einstein worked on the theory slowly and with great difficulty. He needed a mathematics he had not yet learned, the geometry of curved spaces developed in the 19th century by Bernhard Riemann. With help from the mathematician Marcel Grossmann, he eventually found his way through. In November 1915, he presented the field equations of general relativity to the Prussian Academy of Sciences in Berlin. They were 10 interlocking equations describing how matter and energy shape the geometry of space-time, and how that geometry in turn guides the motion of matter and energy. The physicist John Wheeler later summarized the idea in a single sentence. Mass tells space-time how to curve, and curved space-time tells mass how to move. In Einstein's account, a massive body does not reach across empty space to tug on its neighbors. Instead, it gently shapes the geometry around it, and other objects follow the natural paths available within that shaped geometry. A planet orbiting the sun is not being pulled by an invisible string. It is following the straightest path it can find through the gentle valley the sun has carved into space-time. Even light obeys this geometry, because there is no perfectly straight line for it to follow. Einstein's theory made predictions that could be tested. It explained a small drift in the orbit of Mercury that had puzzled astronomers since the 1850s. Mercury's elliptical path slowly rotated by about 43 arcseconds per century, more than Newton's equations could account for. Einstein's equations gave that exact extra amount naturally, with no adjustment. The theory also predicted that light passing close to the sun would be deflected by about 1.75 arcseconds, twice what a simple Newtonian calculation suggested. In May 1919, an expedition led by the British astronomer Arthur Eddington traveled to the island of Principe, off the coast of West Africa, to photograph stars near the sun during a total solar eclipse. The measured deflection matched Einstein's prediction. The news made him famous overnight, and once gravity was understood as curvature, an old question could be asked again with new tools. What happens when curvature becomes severe? The answer would arrive sooner than anyone expected, from the unlikeliest of places. Karl Schwarzschild was a German astronomer and physicist of remarkable gifts. By the time the First World War began, he had already directed an important observatory and contributed to several branches of his science. He was respected, productive, and deeply curious. When the war came, he could easily have remained at home, but he chose instead to join the German army, and by 1915 he was serving on the Eastern Front, where he calculated artillery trajectories and endured the cold and hardship of the field. It was there, in those difficult conditions, that Schwarzschild read Einstein's newly published equations of general relativity. They were dense and complex, and Einstein himself had not yet found exact solutions to them. Most physicists assumed that exact solutions might be a long time coming, but Schwarzschild, working with paper and pencil between his military duties, found one. Within a few weeks of seeing Einstein's paper, he had solved the equations for the simplest possible case: the gravitational field outside a single, perfectly spherical, non-rotating mass. He sent his work to Einstein, who was startled and delighted. Einstein presented Schwarzschild's solution to the Prussian Academy of Sciences in early 1916. It was the very first exact solution to the field equations of general relativity, and it described the geometry of space-time around any spherical body, from a planet to a star. For everyday distances and ordinary masses, it agreed beautifully with what was already known. It explained the motion of planets, the bending of light near the sun, and the small drift in Mercury's orbit that had puzzled astronomers for decades. But hidden inside Schwarzschild's solution was something else, something stranger. The mathematics contained a particular distance from the center of the mass, a radius at which the equations seemed to misbehave. At this radius, certain quantities grew without limit, as if the geometry itself were folding into something the formulas could not easily handle. We now call this the Schwarzschild radius, and the surface it defines is the event horizon of a black hole. For a body the size of the Sun, this radius would be only a few kilometers across. For Earth, it would be smaller than a marble. To reach it, ordinary matter would have to be compressed to almost unimaginable density. At the time, no one quite knew what to make of this strange feature. Schwarzschild himself did not live long enough to explore it fully. He fell ill on the front and died in May 1916, only a few months after sending his solution to Einstein. He was 42. He left behind a quiet, lasting gift, a piece of mathematics that would, decades later, become the doorway through which physics finally walked into the country of black holes. When Schwarzschild's solution first appeared in 1916, most physicists treated the strange radius at its heart as a mathematical curiosity, rather than a physical reality. The equations misbehaved there, but surely, people thought, no actual object in the universe would ever be compressed tightly enough for it to matter. A star like the Sun would need to be squeezed inside a sphere only about 3 kilometers across for its Schwarzschild radius to reach its surface. The Earth would need to be crushed to the size of a peanut. Such densities seemed impossible, the kind of thing equations could describe, but nature would never permit. Einstein himself shared this doubt. In 1939, more than 2 decades after Schwarzschild's work, he published a paper arguing that a true gravitational collapse to such a point could not actually occur in nature. He believed some other effect, some unknown physical process, would always intervene to prevent matter from crossing that threshold. He was, in this instance, mistaken, but his reluctance was understandable. Nothing in ordinary experience prepared the human imagination for a region of space from which not even light could return. And Einstein was cautious about pushing his own theory past the point where its predictions could be tested. The mathematician and astronomer Arthur Eddington, who had confirmed Einstein's light-bending prediction in 1919, was another skeptic. In 1935, he famously clashed with a young Indian physicist named Subramanian Chandrasekhar, who had calculated that sufficiently massive stars at the end of their lives could not hold themselves up against their own gravity and would collapse without limit. Eddington could not accept this. There should be, he insisted, a law of nature to prevent a star from behaving in so absurd a manner. The confrontation was painful for Chandrasekhar, who was young and relatively unknown, and it delayed the full acceptance of his ideas by years. What seems strange now is how slowly the community moved toward what the mathematics had been quietly saying. The term black hole itself did not appear in common use until the late 1960s, when the American physicist John Wheeler popularized it during a lecture in New York in 1967. Before then, such objects were often called frozen stars or collapsed stars, or simply referred to by the unwieldy phrase Schwarzschild singularity. The new name was short, memorable, and a little haunting. It helped the idea settle into the public imagination. But acceptance was not merely a matter of language. It took decades of patient theoretical work, and eventually observational evidence, before most physicists agreed that the universe really did contain such objects. The resistance was not foolish. It was the careful hesitation of people who had been trained to trust their intuitions about what nature would and would not allow. The universe, as it turned out, was more daring than they were. To understand why some stars have no choice but to collapse, it helps to remember what a star actually is. A star is a vast sphere of hot gas held together by its own gravity and prevented from collapsing by the pressure generated in its core, where hydrogen atoms fuse into helium and release enormous energy. For most of a star's life, these two forces remain in gentle balance. Gravity pulls inward. Pressure pushes outward. The star glows, steady and patient, for millions or billions of years. But the fuel does not last forever. When the hydrogen in the core is spent, the star begins to burn heavier elements, each stage shorter and more frantic than the last. Eventually, even these sources run out. Without the heat of fusion, the outward pressure falters, and gravity begins to win. What happens next depends on how much mass the star began with. In 1930, the young Indian physicist Subramanian Chandrasekhar was traveling by ship from Madras to England on his way to study at Cambridge. During the long voyage, he worked out a calculation that would later carry his name. He showed that a white dwarf, the dense remnant left behind by a moderate star, cannot exceed a mass of about 1.4 times the mass of the Sun. Above that limit, the quantum pressure that normally holds a white dwarf up becomes insufficient, and the star must collapse further. This boundary is now called the Chandrasekhar limit, and it marks the first quiet line beyond which ordinary stellar endings become impossible. For a while, it was thought that collapse beyond a white dwarf would simply produce a neutron star, an even denser object in which electrons and protons have merged into neutrons, packed so tightly that a single teaspoon of the material would weigh billions of tons. Neutron stars are real, discovered in 1967 as pulsars by the young astronomer Jocelyn Bell Burnell. But neutron stars also have a limit, somewhere between 2 and 3 solar masses, beyond which no known pressure can hold them up. In 1939, the American physicist J. Robert Oppenheimer and his student Hartland Snyder followed the mathematics further. They published a paper titled On Continued Gravitational Contraction, in which they showed that a sufficiently massive collapsing star must, according to general relativity, fall inward indefinitely. Nothing in the equations stopped the contraction. The outer layers of the star would pass through their own Schwarzschild radius, and to a distant observer, the collapse would appear to slow and freeze at that boundary, while from the star's own point of view, the inward fall would continue toward a central region of unimaginable density. Oppenheimer's paper was published on the same day that Germany invaded Poland, and it received little attention at the time. But it had quietly answered Einstein's doubt. Collapse was not forbidden. It was, for the heaviest stars, inevitable. Of all the strange features of a black hole, the event horizon may be the most often misunderstood. It is not a wall. It is not a surface you could touch or lean against. There is no shimmer in the vacuum, no sudden boundary visible to the eye. If you were to approach one in a spaceship, carefully and from a safe distance, you would see no obvious marker at the edge. The horizon is something subtler than that. It is a boundary defined not by anything material, but by the shape of the paths that light and matter are able to follow. The word horizon is well chosen. On Earth, the horizon is not a place. It is the line beyond which you cannot see, determined by the curvature of the planet and the position of the observer. Walk forward, and the horizon walks with you. The event horizon of a black hole is similar in spirit. It is the boundary beyond which no signal, no particle, and no beam of light can ever reach an outside observer. Events that happen inside it are forever hidden from the universe beyond. Hence the name. For a non-rotating black hole, the event horizon sits at exactly the Schwarzschild radius Karl Schwarzschild had calculated in 1916. The formula is unexpectedly simple. The radius is proportional to the mass. A black hole with the mass of the Sun has an event horizon about 3 kilometers in radius. A black hole with the mass of Earth would have a horizon about 9 millimeters across, roughly the size of a marble, and a supermassive black hole with 4 million solar masses, like the one at the center of our galaxy, has a horizon roughly 17 times the radius of the Sun, still small on cosmic scales, but enormous compared to anything close to home. What makes the horizon strange is not its size, but its nature. In ordinary physics, any boundary can be crossed in either direction. You walk into a room, you walk out of it. A photon enters a window, a photon leaves. But the geometry of space-time near a black hole is arranged in such a way that once you cross the horizon, every direction you could possibly move leads inward toward the center. The outward directions simply do not exist anymore, not because something is pushing you, but because the geometry itself has tilted. It is a little like walking into a valley so deep that every step you take from a certain point onward in any direction is a step further down. You have not done anything wrong. You have not been captured. You are simply following the shape of the land. The universe does not punish you for crossing a horizon. It only quietly rearranges the options available to you. And from the outside, no news of you can ever come back, because no light can climb out. The event horizon, in this sense, is not a door. It is a direction. Imagine, very gently, that a distant observer has sent a small probe toward a large, isolated black hole. The probe is equipped with a simple clock and a light that flashes once every second. For the purposes of this story, we will ignore the violent conditions near a realistic black hole and simply follow what relativity says would happen to the light of the probe as it approaches the horizon. At first, everything looks ordinary. The probe moves inward, the clock ticks, the light flashes once per second, and each flash travels back to the distant observer at the speed of light. But as the probe draws closer to the event horizon, something strange begins to unfold. The observer, far away, sees the flashes arriving slightly slower than once per second, then slower still. The time between flashes grows longer and longer, as though the probe's clock were winding down. This is not an illusion produced by distance. It is a real effect, a consequence of what Einstein's equations say about time in a strong gravitational field. Clocks closer to a massive body tick more slowly than clocks farther away. This is called gravitational time dilation, and it has been measured in laboratories and with atomic clocks flown on aircraft. Near a black hole, the effect becomes dramatic. As the probe approaches the horizon, the distant observer sees its clock slow toward a crawl, the flashes becoming more and more widely spaced, the light of each flash growing redder as it climbs out of the deepening gravitational well. From outside, it looks as though the probe is slowly freezing at the edge. It never quite reaches the horizon. The image of the probe lingers there, fainter and fainter, its final flashes stretched out across eternity. Older physicists sometimes called such objects frozen stars for exactly this reason. To a patient watcher far away, the last moments of the fall seem to last forever, but from the probe's own point of view, nothing so dramatic happens. The clock on board continues to tick at its usual rate. The lights continue to flash once per second. The probe does not feel itself slowing down. It simply falls inward, crosses the event horizon without any particular fanfare, and continues its descent toward the center. Relativity does not grant one of these two perspectives the final word. Both are real. Both are consistent. The difference lies entirely in the geometry of space-time, which has arranged matters so that time itself is not universal. There is something quietly moving in that. Near a black hole, the universe keeps two different accounts of a single journey, and neither is wrong. The traveler falls. The distant observer watches a figure grow still, and in between them stretches the patient geometry of a world in which time, near great gravity, is not one river, but many. The slowing of clocks near a black hole is not a trick of imagination or a feature of science fiction. It is the same effect that physicists must account for every day in ordinary technology. The satellites of the global positioning system carry atomic clocks in orbit about 20,000 kilometers above Earth's surface. Because they are farther from Earth's mass than clocks on the ground, gravity is weaker where they fly, and their clocks tick slightly faster than ours by about 45 microseconds per day. Special relativity adds a smaller correction in the opposite direction, because the satellites are also moving swiftly. Engineers must subtract one effect from the other every day, or the navigation system would drift by kilometers within hours. A difference of 45 microseconds per day is almost nothing in daily life. But it shows that gravitational time dilation is real, measurable, and woven into the ordinary workings of the modern world. Near the surface of Earth, the effect is gentle. Near a neutron star, it becomes significant. Near a black hole, it becomes extraordinary. Just outside the event horizon of a non-rotating black hole with the mass of the Sun, a clock would tick at roughly half the rate of a clock far away. Closer still, the slowdown becomes steeper. As the horizon is approached, the ratio grows without limit, so that a single second on the infalling clock corresponds to longer and longer intervals outside. This is why light emitted from near the horizon reaches distant observers not only delayed, but shifted toward the red end of the spectrum. Its waves have been stretched by the steepening gradient of time itself, a phenomenon known as gravitational redshift. This redshift has been measured in more modest circumstances with great precision. In 1959, two physicists at Harvard, Robert Pound and Glenn Rebka, sent gamma rays upward through a 22-meter tower and measured the tiny shift in their frequency as they climbed out of Earth's gravitational well. The shift was extraordinaire. At the very heart of a non-rotating black hole, the mathematics of general relativity points to a place called the singularity. It is perhaps the strangest feature in all of modern physics, and one of the most honestly humbling. The equations say that matter falling through the event horizon continues inward, and that the inward journey cannot be stopped by any force we currently know. Everything converges toward a central region where density grows without limit and the curvature of space-time becomes infinite. The word singularity is used because the equations themselves at that point cease to give finite answers. They do not calmly describe something strange. They stop describing at all. For a long time, physicists were unsure whether singularities were a real feature of nature or an artifact of particular perfectly symmetric calculations. Perhaps, they thought, the infinities appeared only because Schwarzschild had assumed a perfectly spherical collapse. In the real universe, stars are never perfectly spherical. Perhaps imperfections would save the mathematics. This hope was gently closed off in 1965 when the British mathematician Roger Penrose published a short but powerful paper showing that singularities are not merely the result of special symmetries. Using the methods of what came to be called global geometry, Penrose proved that under very general conditions, once gravitational collapse has proceeded past a certain stage, a singularity of some kind must form. It was a theorem, not a guess. Nature, or at least general relativity, does not seem to offer an escape. For this work, along with related contributions, Penrose shared the Nobel Prize in Physics in 2020. Stephen Hawking, then a young graduate student at Cambridge, quickly extended Penrose's methods and applied them to the universe as a whole. Together, they proved a series of singularity theorems, which suggested that, under general relativity, singularities are not a rare accident. They are woven into the theory. And yet, most physicists do not believe that true infinities really exist inside black holes. The appearance of a singularity is more often read as a warning. It is a sign that general relativity, beautiful and well-tested as it is not the final word. At such extreme densities, the effects of quantum mechanics must become important, and general relativity and quantum mechanics have never been fully reconciled. The singularity, in this view, is not a thing. It is a question. It is the place where our current description of reality softly admits that it is incomplete. There is a kind of dignity in that admission. Science is not obliged to know everything. It is obliged to be honest about where its knowledge ends. And at the center of every black hole, written into the geometry itself, is that quiet confession. Schwarzschild's original solution described the simplest kind of black hole imaginable, one that was perfectly spherical and did not rotate. But real stars spin. They rotate on their axes for the same reason skaters rotate when they pull in their arms. As a massive star collapses, its rotation speeds up, often dramatically. A slowly turning star can become a rapidly spinning neutron star, and a truly massive collapse can leave behind a black hole that carries most of that original rotation with it. For nearly 50 years after Schwarzschild, the mathematics of such a rotating black hole remained unsolved. Einstein's field equations, so elegant in simple cases, became fiercely difficult when rotation was added. The breakthrough came in 1963 from a New Zealand mathematician named Roy Kerr. Kerr was working at the University of Texas at Austin, and he was trying to find exact solutions to Einstein's equations that would describe the space-time around a spinning mass. After months of careful work, he found one. Its structure was far more intricate than Schwarzschild's. It contained not one, but two relevant surfaces, and it described a geometry in which the rotation of the central mass actually dragged the surrounding space-time along with it, like a slow whirlpool pulling water around a drain. This effect is called frame dragging. Near a rotating black hole, space-time itself is set gently in motion by the spin of the mass. An observer close enough would find that they could not remain still, even in principle. To stand perfectly motionless relative to distant stars, they would have to move against the flow of space-time faster than light, which is impossible. Instead, they would be carried along, swept quietly around the black hole by the geometry itself. Outside the event horizon of a Kerr black hole lies a region called the ergosphere, from the Greek word for work. Inside this region, an object must rotate along with the black hole, but it can still escape to infinity if it chooses. The ergosphere is one of the most remarkable features in relativity. In 1969, Roger Penrose showed that it is, in principle, possible to extract energy from a spinning black hole by sending an object into the ergosphere and splitting it, letting one piece fall in while the other escapes with more energy than was brought in. This process, now called the Penrose process, does not violate conservation laws. The energy comes from the rotation of the black hole itself, which gradually slows as energy is removed. Real black holes in the universe are almost certainly Kerr black holes rather than Schwarzschild ones. Rotation is the rule, not the exception. The silent giants of the cosmos are, in their own hidden way, turning, and the very fabric of space-time turns softly with them. Black holes come in a surprising range of sizes, and astronomers today recognize several broad categories. The smallest kind we know of for certain are called stellar mass black holes. They form when a single massive star, roughly 20 times the mass of the Sun or more, reaches the end of its fuel and collapses. What remains is a black hole, typically between about 3 and several dozen solar masses, compressed into a region only a few tens of kilometers across. The Milky Way alone is thought to contain hundreds of millions of such objects, most of them invisible, drifting quietly between the stars. At the other end of the scale lie the supermassive black holes. These are enormous beyond ordinary comparison, with masses ranging from hundreds of thousands to billions of times that of the Sun. They sit at the centers of nearly every large galaxy that has been carefully studied, including our own. The very largest known examples exceed 10 billion solar masses. Their event horizons can be larger than the entire solar system. How such giants grew so massive so early in the history of the universe remains one of the most interesting open questions in astrophysics, and several theories compete to explain it. Between these two extremes lies a more elusive third category, called intermediate mass black holes. These would have masses between roughly 100 and 100,000 times that of the Sun, and for many years they were mostly theoretical. In recent decades, observations have begun to reveal candidates for such objects, including some detected through the gravitational waves they produce when they collide and merge. They may turn out to be the missing link that explains how small black holes grow into giant ones over cosmic time. There is also a speculative fourth category that has never been confirmed. In the 1970s, Stephen Hawking proposed that very small black holes might have formed in the first fractions of a second after the birth of the universe, when pressures were so extreme that even modest concentrations of matter could have collapsed. These are called primordial black holes. Some might have the mass of a mountain compressed into a region smaller than an atom. Whether any exist and whether they could account for some of the unseen mass in the universe is still an open question. What unites this whole family is simpler than it first sounds. In general relativity, a black hole is fully described by only a few numbers: its mass, its rotation, and its electric charge. Everything else about the matter that formed it is forgotten at the horizon. This is sometimes called the no-hair theorem, a name given by John Wheeler in a moment of gentle wit. A black hole, in this sense, is nature at its most austere. Almost everything is set aside, and only the essentials remain. At the center of our own galaxy, about 26,000 light-years from Earth, sits a very dark and very quiet object known as Sagittarius A star. It is the supermassive black hole at the heart of the Milky Way, and its existence was established not by seeing it, which for many years was impossible, but by watching what happened to the things nearby. Beginning in the early 1990s, two groups of astronomers, one led by Reinhard Genzel in Germany and the other by Andrea Ghez in the United States, began a patient long-term study of the central region of our galaxy. Using infrared telescopes that could peer through the thick dust of the galactic disk, they tracked the positions of stars very close to the galactic center. Over years, and then decades, they watched these stars move. What they saw was extraordinary. The stars were tracing tight, elliptical orbits around something they could not see. One of them, called S2, was eventually found to complete a full orbit in just 16 years, whipping past the central object at velocities of thousands of kilometers per second. From the shapes and speeds of these orbits, the mass of the unseen central object could be calculated with growing precision. The answer settled near 4 million times the mass of the Sun, all packed into a region no larger than the orbit of Mercury. Nothing known to physics could account for such a mass so tightly confined, except a supermassive black hole. In 2020, Genzel and Ghez shared the Nobel Prize in Physics for this work, along with Roger Penrose. There is something tender about this discovery. For decades, astronomers watched the silent choreography of stars at the galactic center and quietly inferred the shape of something darker at its heart. The black hole did not announce itself. It left only a signature written in the paths of its neighbors. By reading that signature carefully, patient observers slowly pieced together a picture of an object that refused to be seen directly. Sagittarius A star is, by the standards of supermassive black holes, rather modest. Some galaxies host central black holes 1,000 times more massive. It is also relatively calm at the moment, consuming only small amounts of matter and emitting little light compared with the brilliant active nuclei of other galaxies. Our own galactic center is not a place of cosmic violence. It is a place of quiet gravity, where one of the most extreme objects in physics sits in the dark, holding its court of stars. Every night, when we look toward the constellation Sagittarius in a dark sky, we are looking, without quite realizing it, toward that hidden heart, and toward the stars that have been teaching us for years what must live there. There is a quiet paradox in the study of black holes. The darkest objects in the universe are often found at the centers of the brightest things in the sky. This is not a contradiction, but a consequence of how matter behaves when it falls into a deep gravitational well. When gas, dust, or Even the torn remains of a star drift too close to a black hole. They do not simply fall straight in. Almost always the infalling material carries some sideways motion, and as gravity draws it inward, it begins to spiral. Over time, the material settles into a flattened, rotating disk called an accretion disk, in which particles orbit the black hole at enormous speeds. Friction between layers of the disk transfers angular momentum outward, allowing matter to gradually drift inward toward the event horizon. As it does so, it is squeezed and heated to extraordinary temperatures. The temperatures reached in the innermost parts of an accretion disk can be millions of degrees. At such heat, the gas radiates fiercely, producing not only visible light, but X-rays and ultraviolet radiation that can outshine the stars of an entire galaxy. The first strong evidence for stellar mass black holes came from precisely this kind of glow. In 1964, astronomers detected a powerful X-ray source in the constellation Cygnus, which they named Cygnus X1. Careful observation showed it to be a binary system, in which a normal supergiant star was apparently losing matter to an unseen companion about 15 times the mass of the Sun. The companion was too massive to be a neutron star and too compact to be anything else. It was almost certainly a black hole, and it became the first widely accepted observational case. At the largest scales, supermassive black holes at the centers of some galaxies devour matter so efficiently that their accretion disks become the most luminous, sustained sources in the universe. These are called active galactic nuclei, and their brightest versions are known as quasars. A single quasar can shine with the light of 1,000,000,000,000 suns, yet its light comes from a region no larger than our solar system. For a long time, quasars seemed impossible. Now they are understood as the glow of matter falling into supermassive black holes in the distant younger universe. In some cases, a black hole also launches narrow jets of matter and radiation, shooting outward at nearly the speed of light, stretching across tens of thousands of light years. How exactly these jets are focused and accelerated is still being studied, but the outline of the story is now clear. Black holes are not simply dark. They are often surrounded by some of the brightest, hottest, most restless places in the cosmos, and much of that fire is the long, slow descent of matter reaching the final edge. For a long time, black holes seemed to be the most final objects in the universe. Matter and light could fall in. Nothing could ever come out. The event horizon was a one-way boundary, absolute and uncompromising, and whatever crossed it was assumed to be lost to the rest of the cosmos forever. Then, in the early 1970s, a young physicist at Cambridge began to think more carefully about what happens very close to the horizon, and the picture gently shifted. Stephen Hawking had been working on problems in general relativity for years, including the singularity theorems he had developed with Roger Penrose. But in 1974, he published a short, startling paper with the deceptively simple title, black hole explosions. In it, he argued that black holes are not perfectly black after all. When the rules of quantum mechanics are applied to the empty space just outside an event horizon, the result is that black holes should slowly emit a faint thermal glow of particles and radiation. The effect is now called Hawking radiation, and it came as a genuine surprise even to Hawking himself. The underlying idea is subtle. In quantum physics, the vacuum of empty space is not truly empty. Tiny fluctuations constantly produce pairs of particles that briefly appear and then annihilate one another. Near the horizon of a black hole, Hawking showed the geometry of space-time can separate such pairs before they have time to vanish. One member of the pair falls inward, while the other escapes outward, carrying a small amount of energy with it. From far away, it looks as though the black hole is quietly radiating, and because that radiation carries energy, the black hole must slowly lose mass over time. The effect is extraordinarily small for any ordinary black hole. A stellar mass black hole emits Hawking radiation at a temperature of less than 1/1,000,000th of a degree above absolute zero, far colder than the cosmic background radiation that already bathes it. In practice, such a black hole is not shrinking at all. It is steadily gaining mass from its surroundings. Only very small black holes would radiate quickly enough to evaporate within the age of the universe. For a primordial black hole of the right initial mass, the final stages of evaporation would release a bright burst of energy, a kind of quiet flash at the end of a very long life. Hawking's result has never been directly observed, since the glow is too faint to detect near any known black hole. But it is considered one of the most important theoretical discoveries in modern physics, because it is one of the few places where general relativity and quantum mechanics clearly meet. Black holes, it seems, are not the final word after all. They too can, very slowly, give something back to the universe that made them. Einstein had predicted, as early as 1916, that violent motions of massive objects should send ripples outward through the fabric of space-time itself. He called these gravitational waves. Unlike the ripples on a pond, they would not move through space. They would be ripples in space, gentle stretchings and compressions of distance, traveling outward at the speed of light. For decades, even Einstein wondered whether they could ever be detected, or whether they were so faint as to remain forever beyond reach. The challenge is hard to overstate. A typical gravitational wave passing through Earth changes distances by an amount smaller than 1/10,000th the width of a proton. To measure something so small, scientists built extraordinarily sensitive instruments called laser interferometers. The laser interferometer, gravitational wave observatory known as LIGO, consists of two facilities, one in Louisiana and one in Washington State, each with two long perpendicular tunnels, 4 kilometers in length. Laser beams are sent down each tunnel, reflected off mirrors at the far ends, and recombined. Any tiny change in the relative lengths of the tunnels caused by a passing gravitational wave would shift the recombined light in a measurable way. LIGO operated for years without detecting anything, The instruments were carefully upgraded, and in September 2015, just as the new advanced version began its first science run, a signal arrived. It lasted only about a fifth of a second. It was a faint, rising chirp, exactly the pattern theorists had predicted for two black holes spiraling inward and merging into one. Detailed analysis showed that the signal had come from two black holes, each about 30 times the mass of the Sun, that had collided in a distant galaxy roughly 1.3 billion years ago. In the final moments of their merger, they had converted about 3 solar masses of material entirely into the energy of gravitational waves. That energy had then traveled across the universe and reached Earth as a tiny tremor in the geometry of space itself. The discovery was announced in February 2016, and in 2007, the Nobel Prize in Physics was awarded to 3 of the leading figures behind LIGO: Rainer Weiss, Barry Barish, and Kip Thorne. Since then, dozens of additional detections have followed, including mergers of neutron stars and other black hole pairs. A new branch of astronomy has been born, one that listens rather than looks. There is something deeply sleepwise about that idea. Two enormous, invisible objects met in the dark, long before the Earth had life or oceans, and the universe carried the news of their meeting outward in the form of a faint quiver. Patient instruments listened, and at last the universe was heard. For most of the history of physics, no one expected ever to see a black hole directly. By definition, the object itself emits no light. Even the matter falling toward it, however bright, was thought too small and too distant to be resolved against the glow of the rest of the cosmos. To picture a black hole, scientists relied on diagrams, simulations, and patient inference from the motion of nearby stars. The idea of an actual photograph belonged to a future no one could quite imagine. That future arrived in April 2019. After years of preparation, an international collaboration called the Event Horizon Telescope released the first image of a black hole, or rather, of the glowing matter and shadow surrounding one. The target was the supermassive black hole at the center of the elliptical galaxy known as Messier 87, or M87, about 55 million light-years from Earth. It is one of the largest black holes known, with a mass of about 6.5 billion times that of the Sun, and an event horizon larger than our entire solar system. From that great distance, it appears as a tiny dark speck against the sky, but the Event Horizon Telescope was built to resolve exactly such specks. The trick was simple in concept and astonishingly difficult in practice. 8 radio telescopes scattered across the world, from Hawaii and Arizona to Mexico, Chile, Spain, and Antarctica, were linked together using precise atomic clocks and a technique called very long baseline interferometry. By combining the signals from all of them, the collaboration created what was, in effect, a single virtual telescope as wide as the Earth itself. Only such a telescope could possibly resolve a feature as small as a black hole's shadow at intergalactic distances. The resulting image showed a bright, asymmetric ring of glowing gas, surrounding a central darkness. The asymmetry came from the rotation of the disk. Material moving toward us appeared brighter, while material moving away appeared dimmer, exactly as relativity predicted. The size of the dark central region matched the predicted shadow of a black hole of M87's measured mass. It was not a literal photograph of the black hole, but rather of the silhouette it cast against the light around it. In 2022, the same collaboration released a second image, this time of Sagittarius A, the much smaller supermassive black hole at the center of our own Milky Way. Despite its smaller size, it sits much closer to us, so the apparent dimensions on the sky were comparable to those of M87. Once again, the predicted shadow appeared, ringed by light. After a century of theoretical work, two of nature's quietest giants had finally allowed themselves to be seen in outline through the patient cooperation of telescopes across the world. After all this, it can be tempting to think of black holes as a strange corner of physics, a place where ordinary rules give way and reality grows alarming. But there is another way to see them. Black holes are not exceptions to the laws of nature. They are the laws of nature, followed all the way through to their natural conclusion. Take gravity seriously enough, allow it to gather and gather without interruption, and black holes are what you get. They are not intrusions on the universe. They are part of how the universe works. Almost every theme in this episode meets inside them. The patient pull of Newtonian gravity, the curvature of space-time introduced by Einstein, the slowing of clocks measured to within parts in a quadrillion, the bending of light first confirmed during a 1919 eclipse, the spin of stars carried into the Kerr solutions, the tremor of merging black holes detected by LIGO in 2015, the silhouette imaged by the Event Horizon Telescope in 2019. Each of these threads leads sooner or later to the same place. The black hole is where general relativity becomes most fully visible, where geometry becomes most fully geometry. There is a humility in studying them. The very center of every black hole reminds us that even our best theories have edges, places where they hand the question over to a deeper physics that has not yet been written. The strange marriage of general relativity and quantum mechanics, glimpsed in Hawking's calculation of black hole radiation, remains one of the great unfinished projects of modern science. Black holes mark the borderlands. They are where the map becomes uncertain, and where future generations may find new continents. And yet, for all their strangeness, they have also become surprisingly familiar. Astronomers now find them by the dozens in stellar binary systems, by the hundreds in the centers of galaxies, by the dozens of merger events recorded in gravitational wave detectors each year. The universe is dotted with them quietly the way a forest is dotted with hidden hollows. Most of them do not threaten us. They sit in the dark, holding court over their nearby stars, occasionally swallowing a stray cloud of gas, occasionally meeting another of their kind in a final spiral that sends a faint ripple across the cosmos. When you see a picture of a black hole, the soft orange ring of 87, or the smaller glow of Sagittarius A star, what you're really seeing is a story. A story that began with John Michel's quiet letter in 1783, passed through Einstein's reimagining of gravity, survived decades of doubt, and ended, for now, in patient images and patient signals received here on a small blue planet. Black holes are reminders that even the strangest things in the universe are still part of the universe, and still, in the end, knowable. So now the journey can grow quiet. We began far from any black hole, in an old sky that seemed steady and unquestioned. Newton had gathered the patient logic of gravity into a few elegant rules, and the heavens turned overhead as they always had. From there, we followed a long thread. A country clergyman in 1783 imagined dark stars. A French mathematician quietly reached the same conclusion a few years later, then withdrew the thought. A century passed. Einstein reimagined gravity as the curvature of space-time, and almost immediately, a soldier on the Eastern Front named Karl Schwarzschild found a hidden radius inside the new equations. For decades, even the greatest physicists hesitated to believe such a thing could be real. Then Chandrasekhar, Oppenheimer, Penrose, Hawking, Wheeler, and many others followed the mathematics through, and the universe slowly revealed that the heaviest stars truly had nowhere else to go. The dark stars of imagination became the black holes of physics. Telescopes traced them by the orbits of nearby stars. Gravitational wave detectors heard them collide. The Event Horizon Telescope photographed their shadows. And one quiet object at the center of our own galaxy, 4 million times the mass of the Sun, was finally given its name and its place. You do not need to remember any of this. The names will fade, the dates will soften, the technical details will drift away by morning. What matters is the mood that remains. The universe is a place where gravity, given enough mass, becomes geometry, where time can slow near great weight, where light can be bent, swallowed, and sometimes returned in faint, predicted ways, where even the darkest objects leave signatures in the orbits of their neighbors, in the ripples of space-time, in the silhouettes they cast against distant fire. Outside the room, the Earth turns through space-time without your noticing. The Milky Way wheels slowly around its hidden center, where Sagittarius A star sits in the dark with its court of stars. Far beyond it, in galaxies whose light has traveled millions of years to reach us, supermassive black holes glow at the centers of their own quiet kingdoms. And somewhere, perhaps tonight, two distant black holes are spiraling toward one another, sending a faint tremor outward through the geometry of the cosmos, a tremor that may pass through the earth long after this room has gone still. Yet here, in the small shelter of a night routine, gravity is gentle. The bed holds you. The lamp glows softly. The clock ticks at its own quiet rate. You do not need to solve the universe tonight. You only need to drift within it, held for a little while by a force that, in its most extreme form, can fold the very fabric of space, but that here, now, simply keeps you in place against the turning of the world. The world slows, and so do we. Good night.